Dear students, the next type of microscope that we are going to study is atomic force microscope. So it is a type of scanning probe microscope that records the force between probe and the specimen. It has three basic components: probe, positioner and a processing unit. In the figure you can see that there is a probe, there is a positioning element, laser beam and detector processing unit. An AFM has a pointed probe attached to the rectangular base called cantilever. So there will be a cantilever beam, and at the end of that cantilever the probe or analyzer is attached. The positioning of the cantilever with respect to the specimen is achieved by the piezoelectric elements called scanners. The laser beam is focused on the cantilever that has a highly reflective surface. So after receiving the laser beam, it is made to scan on the detector, and this is a highly reflective surface. The laser beam reflected off the cantilever is focused on the position sensitive photodiode quadrant. The cantilever is scanned over the sample surface in a raster pattern. Any deflection in the cantilever as a result of sample interaction causes displacement in the laser spot on the photodiode. This displacement signal is analyzed to calculate the deflection in the cantilever. So imaging can be performed in two ways, that is either constant force mode or constant height mode. In constant force mode, the distance between the tip and the specimen is allowed to change, and the force obtained in the external circuit is maintained constant. That is, the probe, it will be electrically conducting material. So the electricity is passed between the sample and the probe, and the force obtained is maintained constant in the circuit. So if the force has to be maintained constant, the variable is to be done is the electric current has to be varied. And next one is constant height mode. In constant height mode, the height or gap between the sample and the probe is maintained constant, and the force between the tip is allowed to change. So this is how the analysis is carried out on AFM in two different types. So this is a type of microscope similar to that of SPM, scanning probe microscope. So this is also a type of SPM itself. The advantages is it does not involve tedious sample preparation. The sample to be analyzed can be simply placed on the smooth surface and we can scan. It is possible to record AFM smooth images in solution. So we can take the images obtained, we can record it for our purpose, for our analyzing purpose. AFM tip can be used to mechanically manipulate the specimen at very high spatial resolution. So the tip present in the AFM, we can use it to manipulate the specimen based on our requirement. Next is disadvantages. The scanning speed is less. The instrument is highly dependent on the probes. So if the probes are working correctly, then it is good. Otherwise, the entire operation we cannot be fruitful. It is limited to maximum height of 10 to 20 micrometers and maximum scanning area of about 150 square micrometer. So the maximum height should be between the specimen and the pointer should be between 10 to 20 micrometers. So if the distance is beyond this range, then we cannot operate AFM. Also, the scanning area is limited to 150 square micrometer. The next type is the X-ray diffraction, or we call it as XRD. A beam of X-rays directed at a crystal interacts with the electron of the atoms in the crystal. The electrons oscillate under the influence of incoming X-rays and become secondary source of electromagnetic radiation. The secondary radiations are scattered in all directions. The waves emitted by the electrons have the same frequency as that of incoming X-rays. In the figure you can see that there is a crystalline material, and we are going to apply strong electromagnetic radiation, that is, we are going to apply X-rays on that crystal. So the X-rays pass through the crystal, and some of the X-rays get scattered and some of the X-rays pass in the same direction as that of original direction. So the both the scattered X-rays and the original X-rays, they will have the same frequency as that of original incident X-rays. So by analyzing the scattered X-rays, we can find out the information present in the crystalline material. So the essential parts present in this is, one is X-ray tube. It is the source which generates X-rays. The next one is incident beam optics. That is condition of X-ray beam before it hits the sample. The next is genometer. This is the platform that holds and moves the sample, optics, detector and tube. So it is a holding device. It holds the specimen. It will hold the detector and tubes. Next one is receiving side optics. That is the optics or condition of X-rays after passing through the crystalline material. Detector counts the number of X-rays scattered by the sample. Detector, it is the one which receives the scattered electrons, and we can analyze through the detector. The principle of working is, in single crystal X-ray diffraction measurement, a crystal is mounted on the genometer. It is used to position the crystal at selected orientations. So the crystal is illuminated with a finely focused monochromatic beam of X-rays, producing a diffraction pattern of regularly spaced spots known as reflections. So the sample to be tested, it is fixed on the genometer and it is applied with high intensity X-rays. So this high intensity X-rays hits the specimen and it will pass through it and it will scatter. The two-dimensional images taken at different orientations are converted into three-dimensional model of the density of electrons within the crystal using mathematical method of Fourier transforms combined with chemical data known for the sample. So after receiving the diffracted or scattered electrons, this is analyzed by using complex methods of Fourier transforms, and the information can be obtained based on the study carried. The advantages is that minimal sample preparation is required. So even the sample preparation is very less, we can use this method. XRD units are widely available. That is, XRD instruments, they are present in each and every institution that carries science research work or any science related projects. Data interpretation is relatively straightforward. So the data interpretation or the analyzing of the scattered beams, it is straightforward. No, it is not difficult to analyze the scattered electrons. It can be used to identify unknown material or unknown mineral present in the sample. We can easily analyze. The disadvantages is, it is used to identify unknown powder material. The sample should be homogeneous. So if the sample is homogeneous, we can analyze the unknown mineral. Otherwise, we cannot analyze. Next is, typically XRD analysis require access to standard reference data. So we need to refer some standard reference in order to analyze the crystalline material, and the samples often require grinding them down to a powder to analyze. So before analyzing, we have to grind the crystalline material and then we have to analyze. The applications is, it is used to identify crystalline phases and orientation. It is also used to determine structural properties such as lattice parameters, grain size, XP-Truxy, phase composition, preferred orientation, etc. So we can analyze all these on XRD to measure thickness of thin films and multi-layers. So if any crystalline material have different layers in it, we can measure the thickness of the multi-layers. So it is also used to determine atomic arrangement. So we can use this method to find the atomic arrangement of any crystalline material. So these are the applications of XRD. Thank you guys.